For this week's SAT 22 question, we got squirrels. So let's take a look here. A model estimates at the end of the year from 2015 to 2020, number of squirrels in the population was 100%, 150% more than the number of squirrels in the population at the end of the previous year. The model estimates that at the end of 2016, there were 180 squirrels in the population. That's a lot. Which of the following equations represents this model, where n is the estimated number of squirrels in the population t years after the end of 2015, and t is less than or equal to 5? And you can see that we have a variety of exponential equations to choose from. Let's take a look to see how we did. Dun, da, da, da. Ooh, so you can see that a little teeny bit over half of us chose answer choice B, and answer choice B is in fact the correct answer. However, this is our lowest result so far of the 7 weeks that we've done this so far. And you can see place number 2 is answer choice C, which is, as you'll see, I will mark this one off as one of the distractors when we get into the actual solution. And then as far as difficulty, we said that this was, I would say, medium to the easier side, even though, as you can see, about half of us got it right. About half, almost 50-50 here. Here, let's go ahead and take a look at the solution. So now, what I am going to say here, get my color straight here, is that we're working with a couple of years. We're looking at the first year being 2015. This is where t is equal to 0, so keep that in mind. And then 2016 is where t is equal to 1. How do I know that? Because take a look at the last part of the sentence here. It says, where n is the estimated number of squirrels in the population t years after the end of 2015. So at t is equal to 0, you're still in 2015. Okay, and then specifically at 2016, it says, where is this? 2016, there's 180. So this year gets the 180. So in other words, if I stick in the number 1, I'm supposed to get 180. It's an ordered pair. Let's say, looks like this, 1 comma 180. All right, so I'm just going to test this out. For example, if I were to plug in a 1, and this is why I'm going to eliminate both of these two right here. If I stick in the number 1, then this one is gone. And the reason why is because you would be multiplying 180 times 1.5 to the first power, right? This would be 180 times 1.5, and that's going to be bigger than 180, so this is going to eliminate this question, this example, or this answer choice, and then likewise, for the same exact reason, we're going to get rid of D. This is going to leave us with either answer choice A or answer choice B. I mean, even more, I could actually just answer the question here from plugging in the number 1. If I plug in the number 1 here, I would get, let's see, I would get 72 times 1.5 to the first power. Let's see if I get 180 right here. All right, so this is, we'll probably need a calculator, unless you can, oh, no, that's the wrong one. Let's do this one and clear all this stuff out. And 72 times 1.5, and we get 108. Okay, well, again, there we go. So this has given us 108, which is not the answer choice, which, well, there you go. Process of elimination has to be answer choice B. But, I'm going to take you through why it actually is answer choice B. Again, if you go ahead and stick in the 1 comma 180, 72 times 2.5 to the first power, we should get 180 this time. Let's pull up the good old Desmos. So 72, that's a 5. 72 times 2.5. Oh, there you go. There's the 180. Voila. There's our answer choice. Okay, so let's actually see what's going on here. Let's dive a little bit deeper. So each one of these is an example of what is called exponential growth. And what is happening is that we're going to, let's say we're going to start with some sort of population, and multiply it by a certain percentage, and it says that our population is going to grow by 150% more than that original population. Now, rather than starting with this 180, I'm just going to make up a fake population here. Let's say our fake population starts at 100. Okay, so now I'm going to multiply this by 150%. So if I multiply this by 150%, in order to actually do that calculation, percent means out of 100. So I'm going to divide this by 100. And when I divide by 100, we know that that's equivalent to just moving the decimal place over 2 places. So this is equivalent to move this decimal place right here as 1.5. So really we have 100 times 1.5, which is equal to 150. And actually, let me just put this underneath here like so. 150. Okay. But that's not what the population is, because remember what it says right up here is that the number of squirrels is 150% more than the number of squirrels in the previous year. So you have to add this back to the original population here, which is 100. Now, of course, that makes 250 squirrels. Again, this is the fake 100. I'm kind of going through the process of where the equation comes from, okay? So rather than actually work this out and get 250 total squirrels, notice that we have a common factor of 100 here. That I'm going to just kind of pull out. I'm going to factor this thing out and rewrite it as 100 times, and this is going to be 1.5 plus 1, right? If I were to distribute this back through, here's the expression that I would get. And what I want to call your attention to here is that this 100, that's the original population, the original amount. The 150 is our rate, which we usually use as represent with the letter R, and then we're adding 1 to it. And this is what happens whenever we're factoring out the 100, which is the population. That happens twice right here, plus 1. Okay, so then, of course, I can just simplify this as, where's my blue crayon? Here we go. Simplify this as 100 times 2.5, and you can see that 2.5 just come up right here in this equation. Okay, now then, let's see. If I were to do this again, so let's see where the whole exponent part comes from. Let's say that I do this again. So this is my new amount at the end of the year, 100 times 2.5. Okay, so now my population at the end of the next year has to be 150% more than that. So I'm going to take this and I'm going to multiply it times 1.5. And then I'm going to add it to the previous population. Now, remember that the previous population now is this 100 times 2.5. So 100 times 2.5. And rather than work it out, I'm going to do the little fancy factoring one more time. So notice that both of these terms have a 100 times 2.5. So I'm going to pull that guy out. This is going to be 100 times 2.5. And then whenever I do my little factoring, divide both of these things by 100 times 2.5. I have the 1.5 for the first term, plus, and then if I divide this by 100 times 2.5, I get just plus 1. In the brackets there, you can see at the end, we have another 2.5. So I'm going to add that up, 100 times 2.5 times another 2.5. And then rewriting that repeated multiplication is represented by an exponent, so 100 times 2.5 squared. And then if I do it again, this is going to be to the third power, and then to the fourth power, and so on. And then that's where these little exponential equations are going to come from. So generally speaking, exponential growth looks like this. We can use the little n right here if you want to. So I'll say n is equal to our population. And then inside the parentheses here, I'm going to do 1 plus the rate, and then I'm going to raise it to the t power. And so that's where the actual exponential growth equation comes from. When you get into Algebra 2, you're going to refine this just a little bit. Instead of having it grow only at the end of the year. You're going to have a continuous growth, and the continuous growth is where we get the good old-fashioned letter E. Where is the E in this calculator? Let's see. Can I find it? It's probably just under the alphabet. E, and then you can see this 2.718 business. That's where it comes from. If you do continuous growth, you'll see what that's all about in Algebra 2.